All right, let's talk about object-oriented programming. Chances are you've heard the term, or maybe you've seen the acronym OOP and thought, that sounds a little complicated. Well, you're in exactly the right place. Today, we're going to pull back the curtain on this huge concept and show you why it's way more intuitive than it sounds. So, let's just jump right in. The thing is, OOP is absolutely everywhere. It's in the apps on your phone, the websites you visit, even the most complex software systems in the world. And while it might sound really academic, the main idea is actually something we can all understand. We're going to break it all down piece by simple piece. So what is Ubi, really? Well, at its heart, it's just a way of thinking about code. Instead of writing one long, messy list of instructions, we create these little digital objects that act like things from the real world. Think a user, a product, a bank account. This way of organizing things makes our code cleaner, easier to reuse, and so much easier to handle as our projects get bigger. Okay, to really wrap your head around OOP, you've got to understand two key building blocks, the class and the object. And honestly, the best way to think about it is with a house blueprint. A class is the blueprint. It defines all the things a house should have, like doors, windows, and a roof. An object, that's the actual house you build from that blueprint. And just like a real blueprint, you can build a whole neighborhood of different houses, lots of objects, all from that one single class. All right, with that foundation, let's build on it with the first of the four big pillars of OOP, inheritance. Just think of it like creating a family tree for your code. It's all about making connections and building a clear hierarchy. Really, it all boils down to this simple idea, the is-a relationship. Inheritance lets a new class, or a child class, automatically get all the features of an existing parent class. For instance, a student is a person, or a car is a vehicle. This is an incredibly powerful way to stop writing the same code over and over again. This diagram makes it super clear. We have a general person class, right? It's got the basics, like a name and an age. Now, both the student class and the teacher class can inherit those basics, but then they add their own unique stuff. A student has a program they're in, and a teacher has a salary. We don't have to redefine name and age every single time. It's efficient. So, what does this actually look like in code? Well, in Java, it's all thanks to one simple keyword, extends. You can see it right here. The dog class extends the animal class. That one little word instantly gives our dog object all the abilities of an animal, like make sounds method, while still letting it have its own special dog-like things, like a bark method. Okay, on to our second pillar. Now, this one has a bit of a scary-sounding name, polymorphism. But trust me, the idea behind it is actually super simple and really, really powerful. You know, if you just break down the word, it tells you everything you need to know. Poly means many, and morph means forms. So polymorphism, it's just the ability for one single action to have many different forms or behaviors depending on what's performing it. One name, many outcomes. Here's a fun way to think about it. Imagine you've got a bunch of different animals, and you tell each of them to speak. You're not going to get the same sound from all of them, right? A dog will woof, a cat will meow, and a duck will quack. They're all doing the same action, the speak action, but the result is unique to each animal. That is polymorphism in a nutshell. And here's how that translates into a real-world coding example. Let's say a parent bank class has a method called getInterest, but each child class, SBI, ICICI, Axis, can provide its own unique version of that method to return its own specific interest rate. Same method name, totally different results for each bank. Now, when you're coding in Java, you'll see polymorphism pop up in two main flavors. There's method overloading, which is when you have different methods with the same name inside the same class, but they just take different inputs. Then there's method overriding, which is what we saw with the banks, where a child class provides a specialized version of a method from its parent. All right, our next two pillars, encapsulation and abstraction, kind of work together as a team. Think of them as the protective shells of our code, all about managing complexity and keeping things safe and simple. Let's look at each one. First up, encapsulation. It's literally about putting your data and the code that works on that data into a little capsule, the class, and protecting it from the outside world. You can't just reach in and mess with the data directly. No, you have to use the specific methods the class gives you. This is huge for preventing bugs and keeping your data safe. Then you've got abstraction, which is kind of the other side of that same coin. It's all about hiding the messy, complicated stuff. When you drive a car, right? You just use the steering wheel and pedals. You don't need to know exactly how the engine is firing or how the transmission is shifting gears. Code abstraction is the same idea. It gives us a simple, clean interface to use while all the complex logic is hidden away. Okay, so we've got our 4 pillars down. Now for the fun part. Let's see how all these pieces come together to build the actual complex systems we use every single day. This is where it gets really interesting. So far, we've talked a lot about that is-a relationship. A dog is an animal, but objects also have has-a relationships. A car has an engine. A college has students. This describes how bigger objects are built up from smaller ones, and there are a few different flavors of this. And this has idea comes in a few different strengths. The weakest is association, where 2 objects are linked but can exist without each other, like a manager and a swipe card. A bit stronger is aggregation. A college has students, but if the college closes, the students don't disappear. And the strongest is composition. A building has rooms. If you demolish the building, the rooms are gone too. Their fates are tied together. All right, we've covered all the big theories. Now, for all you students out there, let's switch gears. We're going to do a quick fire round on some key things that you are almost guaranteed to see on your exams or in job interviews. Pay attention. Here are some Java keywords you absolutely have to have locked in your brain. We've talked about extends for inheritance. Super is how a child class can call methods from its parent. And try-catch blocks are your best friend for handling errors gracefully so your program doesn't just crash. Okay, write this one down because this is a classic exam question designed to trip you up. You can't make an inherited method more restrictive. If a method is public in the parent class, it has to stay public in the child class. You can't hide it or make it private. The child has to honor the parent's contract, and trying to change that will give you a compiler error every time. Here's another one that gets a lot of people. I'll give you a second to think about it. Can you override a static method?
The answer? A hard no. You just can't. And the reason is simple. Overriding is all about objects, about specific instances. Static methods don't belong to an object. They belong to the class itself. Since there's no object instance involved, the whole idea of overriding just doesn't make sense for them.
So there you have it. From classes and objects to inheritance, polymorphism, and all these other powerful principles, we've really unpacked the core ideas of OOP. These aren't just programming rules. They are literally the blueprints for building entire digital worlds. So the only real question left is, what will you create with them?